Okay, we'll go ahead and get started. And we really appreciate you joining us. And we're also glad to be back with with our series, our webinar series. We've been away for a few months with all the holidays behind us, so we are glad to be back. So this webinar series will be on solvent dyes. So thus I've sort of renamed the series to Colorants 101 because we're going outside the pigment domain and into the into the colorants area. So as we've done before, I will record this webinar series, and those that are in attendance will receive the link as well as the PDF of the presentation as well. If you do have any questions, please go ahead and use the chat box, and I will address those at the very end. So let's go ahead and get started. And so as we've talked about, dyes are the other half of the colorant world. We've talked a lot over the last year and a half or 2 years or so about pigments. However, it's always nice to complete the colorant portfolio by talking about dyes. So a little fun fact that between dyes and pigments, they're about 9,000 in total in number today from a commercially active aspect. And just to dig down in a little bit more on this one, we like to go into a little bit deeply. So why is it that there are so many in use today? Well, the first reason is that there's a wide requirement of a wide variety of tints and hues that are needed for all of the applications where colorants are used. Just take a look around your store shelves, your home, the car lots. So there's a lot of different areas where there are requirements for that, for a unique colorant of a particular hue and tint. The chemical compositions of the end substance that needs to be colored. So not every colorant will work in every final application. So we have to match up both the chemistry of the colorant as well as the chemistry of the end application. There is, as we know, a direct relation of color to the molecular structure of that particular colorant. For dyes, the first commercially viable dye was a mauve in color, which was discovered in the 19th century by a British chemist named Perkin, and he used that for coloring wood and silk dyeing. So with respect to polymer dyes, this chart that I have here is primarily targeted at polymer soluble dyes, so that we can dive down a little bit more specifically into the type of solvent dye that Sudarshan is producing. So the polymer soluble dye is estimated to be about 4,700 tons. With a value of about $180 million in the U.S. And in the chart, it gives a feel for the popularity or the volume of each of the top color indexes. So you'll notice that the solvent red 135 is by far the most important solvent dye in the industry, about 3 times as large as the next largest solvent dye, which is the solvent yellow 114. Next in line would be the solvent blue 104. And then all the others follow in line after that. And then there are some general categories at the very end where we pull together other reds, other yellows, and other blues, and then others. So just a couple of footnotes with regards to this. The first one is that we see the solvent yellow 114 is growing at the expense of solvent yellow 93. And that's primarily because solvent yellow 93 cannot be FDA certified, whereas the solvent yellow 114 can in there. The second footnote is with respect to the solvent blue 104. It has additional volumes as it is an intermediate for other dyes like solvent blue 45, acid blue 80s, and others. And then the very last category that I have here, it's called shade others. This makes up some oranges, violets, and greens that are much more small in volume, so they get into that other category. So again, just to refresh you that the volumes that I have here are referring just to the polymer application. A lot of these color indices that are up here are also used in other areas such as wood stains, printing inks, but these are not included in the volumes that you see here. So for solvent dyes, a solvent dye is, as the name implies, is a dye that's soluble in organic solvents, insoluble in water. And they are used to color organic solvents, hydrocarbon fuels, waxes, lubricants, plastics, and other hydrocarbon-based non-polar materials. Light fastness ranges from poor to good depending on the chemistry of the dye. So basic dyes would be on the poor end of light fastness, whereas metal complex-based dyes would be on the good end. Solvent dyes are also used as a gold imitation and other transparent metal effects for polyester films. Think glitter here. They are also used for marking inks, inkjet inks, wood stains, and other glass colorations. For dyes, they also take on the same type of color index naming schemes as pigments, obviously except for the beginning letter being a S for solvent, followed by the color letter and the chemistry number. So for example, you have solvent red 135, solvent yellow 93, and solvent orange 60. For plastics, solvent dyes solubilize in the polymer of interest, whether that be PET, polystyrene, or any other plastic in here. So solubility in the polymer is key for these types of dyes. Solvent dyes have high chroma, very high transparency. They do have a potential for bleeding or migration. They are very good fastness to heat and good fastness to light because of the metal complexing that we talked about earlier. Color shade consistency is very good, and you'll see why in a moment. These offer a low use cost. A little bit goes a very long way. These are polymeric specific, as I mentioned, as far as the solubility is concerned. One potential pitfall to be aware of is that they tend to have that impact of TiO2 photodegradation. And the data here I have is just one example of the solvent yellow 93 at taking a look at the Xenon 4000 weatherability here, and at the full tone we see that the color falls off greater than 3 at 700 hours, whereas when the solvent dye is mixed with the TiO2, it falls off after 300 hours. And Similarly to pigments, the properties of dyes are determined by their chemical structure. So that's nothing different there. So I went back to some of the pigment slides that I've used in the past, and I wanted to do a little bit of compare and contrast. So for pigment, we've talked about this in the past, where 75 to 80% of the pigment performance is based on the chemistry itself, while the remaining 20 to 25% is based on the finishing treatment that is applied to that particular pigment, whether it be for opacity or for gloss, whether it be a drying process, a milling process, or a surface treatment. So two parts of the synthesis result in the performance of pigment. Compare that to dye, whereas 100% of the dye performance is on the chemistry itself. There is no finishing or surface treatment used, so 100% of the performance is only on the chemistry. So the colorant selection process is not different than what we've seen in the past. Color and effect, of course, is where one would start in the selection process. For solvent dyes, certainly the application has to be considered, what types of polymers are being used, heat stability, if there's any kind of interactions and formulations, like I mentioned with the TiO2, light fastness and weather fastness is always of consideration. Performance is the next area. I mentioned about the potential migration resistance, how much is required there, as well as distortion or nucleation. For pigments, we typically want to make sure we understand the dispersibility and particle size with respect to pressure rise for fibers and film transparency. For solvent dyes, these are not applicable because they will be completely dissolved in the polymer, and there will not be any physical particles remaining to have an issue in these two areas. Compliance is always something to consider when selecting a colorant. And of course, the cost as well as the value in use of that particular colorant. So really not a whole lot of difference with respect to solvent dyes versus any other colorant that you might choose. So as you know, it's a balancing act. Just like on the pigment side, we need to be able to balance the must, the wants, and the nice to haves with respect to that colorant and the final application performance required of that colorant. Red and yellow solvent dyes are often in the azochemistry category, whereas greens and blues tend to be in the anthraquinone. So there are a number of other chemistries that result in the variety of colors that are seen in the solvent dye portfolio. And here are just a few that are available in the marketplace. So going back to some other slides I've used in the past, just to continue that comparison of a pigment versus a dye. So with a pigment, there's always going to be a physical solid particle in the part or the film that is ultimately being colored. And that physical solid particle will always scatter, absorb, reflect, and then ultimately transmit the light through that particular specimen to provide that color. Compare that to a dyed solution or part where there are no physical particles to interrupt that light transmitting through the specimen, so that all of that light is transmitted through the part, and you see that color. And then lastly, a little bit more of a visual aspect to the comparison. The pigments will be a physical solid particle, whereas the dye will dissolve completely in that solution that is being used. So to continue the comparison, here what I've done on a little bit more of a practical aspect of it, I'm comparing in similar color spaces the transparency of a solvent dye versus a pigment. In this comparison, I'm comparing an organic pigment, a red 53-1, with the solvent red 135, which is on the right-hand side. And in each case that I'll present, the amount of colorant is always the same, whether it's a pigment or the dye. So you can see on the right-hand side with the solvent red 135, the lines behind the chip are very clear and crisp, whereas the organic pigment red 53-1, you start to see very little of the lines showing through the chip. Moving from the red space to the orange space, here I am comparing an orange color that I created using that same red 53-1 with a yellow 62, I'm sorry, in a 75 to 25 ratio, and comparing that to the solvent orange 60 on the right-hand side. And once again, you see very clear, crisp lines through the solvent orange 60 chip, whereas the pigmented chip is the lines are less clear and less seen in here. And then lastly, moving to the yellow space, where here is the comparison to the pigment yellow 62 and the solvent yellow 93. Here we get a little bit more of or a little bit less of a distinction between the two, but if you look closely, you can definitely see that the solvent yellow 93 chip, the lines are very clear and crisp through the chip, whereas the pigment yellow 62 is a little bit more fuzzy and less apparent through the chip. And it is interesting to note that taking advantage of that clear, crisp transparency of the solvent yellow 93, it just made our color of the month for February that much of interest for this webinar series. So this color of the month called Lemon Zest was created with the solvent yellow 93 and an iridescent gold mica 4195 in a 25 to 75 ratio. So you can see the transmitted color, so you can still see through the chip here, and then on the reflected color, the mica then comes through very nicely to see those sparkle effects in there. So you get two different types of color effect with one color formulation. So there are other types of dyes. Just a brief review of what they are. Reactive dyes are used for coloring cellulose acetate and some other synthetic fibers. Direct dyes are used for coloring cotton wool and cotton silk combination. Basic dyes, they are used for coloring paper. Vat dyes are used for coloring fibers, and acid dyes are used for coloring animal fibers. It's interesting to note, as the note at the bottom indicates, that some vat dyes are also considered a pigment, such as pigment orange 43, which is the same as vat red 15, and pigment red 181 is also considered vat red 1. So they do some chemical molecules then cross both the solvent, cross the dye and the pigment line there for the use, depending on where they are used. So jumping ahead from that, the volume chart that I showed earlier, I've just pulled some of those off of that chart onto this chart to give you an idea of what chemical family they belong to, as well as their chemical structure and their color family. Those that I've highlighted in yellow are the ones that I'll give a little bit more details with following this chart here. So as I mentioned, the solvent red 135 is the highest volume solvent red or solvent dye in the polymer area. It is a bright red powder used for a variety of plastics. It'll be highly recognized because it is the prime colorant for the car taillights. So next time you get in your car, you'll think of solvent red 135 when you see the car in front of you put on its brake lights. It has very good light fastness with a rating of 6 to 7, very high heat resistance. And as I mentioned, it is the highest volume solvent dye, about 3 times the next largest solvent dye in the category. And for Sudarshan, this makes up our first entry into the Sudasol brand of solvent dyes, with its identification being the red 6706. In volume is the solvent yellow 114. This is a green shade yellow in color. Again, a variety of polymers are suitable for this solvent dye. And again, it is starting to beginning to replace solvent yellow 93 because of that food contact inability for the solvent yellow 93 chemistry, while the solvent yellow 114 chemistry is food contact safe. It has good light fastness with a rating of 70 and high heat resistance. The Sudarshan product in the Sudasol line will be launched later this quarter. Third in line in terms of volume is the solvent blue 104. It is blue in color, has a variety of uses besides plastics: ballpoint pen ink, toning printing inks, and as well as plastics. It has good light fastness with a rating of 7, as well as good heat resistance. And our Sudarshan Sudasol product will be launched in the second quarter of this year. So we look forward to that. Solvent yellow 93, one we've been talking about all along. It's a bright yellow powder, does have good light fastness at 7 and heat resistance. However, it does have that one restriction with respect to food contact. The Sudarshan product is the Sudasol yellow 6501. Solvent violet 19. Solvent violet 13. This is a brilliant violet powder in color, primarily used for polystyrene, polycarbonate, and PMMA. It has a decent light fastness at a rating of 6 and also good heat resistance. The Sudarshan product will be launched in the second quarter of this year. Solvent orange 60. This is a yellow shade orange in color. A variety of plastics are where it is very suitable for, with good solubility. Very good light fastness with a rating of 7 to 8, as well as high heat resistance. The Sudarshan product is Sudasol Orange 6601. Solvent Blue 122. This is a dark blue in color, and it is also used for a variety of printing inks and other applications like rubber, gasoline, and waxes, as well as plastics. It has a medium to good light fastness with a rating of 6. However, it does have a lower heat resistance than the others that we've discussed already, with a rating of 240 degrees C. So consider that with respect to your technical requirements for your application. The Sudarshan product will be launched later in this year in the fourth quarter, so we are also looking forward to that one as well. Solvent Green 3. This is a blue shade green in color, a variety of polymers. It is suitable for a variety of polymers, especially polystyrene, ABS, polycarbonate, and others. A very good light fastness rating with a rating of 6 to 7 and good heat resistance as well. And our Sudarshan product will be launched in the third quarter of this year. So you can see we will have a very busy year in the Solvent Dye brand to bring to your for your needs. And lastly, Solvent Red 179. This is a blue shade red in terms of its color. Can be used for a variety of plastics. It does tend to have a better solubility than the Solvent Red 135, with a good light fastness, a little less than the 135 at a rating of 6, but also very good heat resistance at 300 degrees C. The Sudarshan product is Sudasol Red 6721. So as far as synthesis of solvent dyes, what is actually being done in the synthesis is that an aromatic ring structure is coupled with a side chain, and that side chain is required to impart the color. A little bit of terminology here with respect to solvent dyes. So we talk about that aromatic ring as being the chromogen, and they take on the structure of a benzene, naphthalene, or anthracene in terms of its structure. The side chain that I spoke about is referred to as the chromophore, and in other terms, it is the color giver. So the chromogen requires this chromophore to be able to provide the appropriate color for that particular chemistry. So the chromophore can take on the chemistry of an azo, carbonyl, carbon nitrogen, a nitro, or sulfur. So you can see you have a lot of options to create that color that you're looking for with that given chemistry. And lastly, in the process, the chromogen and chromophore structure that I spoke about, it may not be enough to impart the required solubility in the polymers that we would like them to go into. So a bonding affinity group might also be added to that chromogen chromophore structure to improve that solubility. And they can take on the structure of an amine, hydroxyl, carboxyl, or sulfonic. So if a bonding affinity group is used, it's very important that as they are used as part of the classification of the dyes. So like pigments, the dyes are synthesized in a reactor. They're filtered, dried, and blended with other additives that produce the final product. The synthesis step is, again, a variety of reactions depending on the raw materials that are being used to create that chemistry. They can take on sulfonation, halogenation, coupling, so a variety of syntheses that are being used to create that chemistry. As far as separation, it might be a distillation process or precipitation or crystallization. So again, a variety of steps along the way depending on the chemistry that we're trying to create. So as I mentioned, the Sudasol is one of our newer brands in the Sudarshan portfolio of colorants. And so we're happy to have them on board. And we are also happy to see the expansion of that line throughout the rest of this year. So as I mentioned, some of the products that we've already launched in our line are Solvent Red 135 is the Sudasol Red 6706. The Solvent Yellow 93 is the Sudasol Yellow 6501. The Solvent Orange 60 is the Sudasol Orange 6601. And lastly, the Solvent Red 179 is the Sudasol Red 6721. So up next, we are going to shift gears a little bit and go back to another application-specific webinar where we're going to talk about colorants for ink applications. That will be held on March 29th, the last Tuesday of the month. And like always, you'll receive a Teams webinar invitation for the registration about a week ahead of the webinar series. And then continuing in the future series in April, we will do a part 2 on mica effect pigments, as a lot has happened since we first brought you the part 1 in late of 2019. So I'm only just one part of the North American team. We are all here to support you and answer any questions that you might have, or advise you in any sample selection. So please feel free to reach out to any one of us, and we'd be happy to help you in your needs. With that, I'd like to open it up to any questions that you might have. And I am going to switch over to see the let's see if there's any questions in the chat box. Okay, there's a question on the FDA approval. So right now we have 3 of our dyes, the Solvent Red 135, the Solvent Orange 60, and the Solvent Red 179. They are currently in the FDA approval process right now. And so we are looking forward to getting those final approvals. It's hard to say the timeline when you're talking about the FDA approvals, but suffice it to say that they are in process to get them. And so as soon as we have that information, we will be glad to pass that along to you. Another question was, how does pastel photo degradation differ from regular light degradation? In this particular case, it is the photocatalytic activity of the TiO2 that is interfering and reacting with the chemistry of the dye to cause a degradation of the colorant in there. So it is different, whereas regular light degradation is degrading the actual chemistry, the molecule. The TiO2 photo activity actually reacts with the chemistry, causing that degradation of the color. Another question was, what do you use to standardize the strength of your solvent dye products? Obviously, I can't go into specifics on that one, but suffice it to say that all of our products are adhered to a very tight strength application. So we have on our TDS and our spec sheets a plus or minus 5% strength against our standard. Suffice it so that all of our products are within in the appropriate control of our standard product. Are there any other questions?